So for this proof style problem, what are we asked to show? We're given a function, x raised to the fourth plus 3x plus 1, and we want to show it has exactly 1, 0 on this closed interval running from -2 to -1. Thinking the way through this, if we have to show it has exactly 1, 0, first thing that we have to show is that it has at least 1, 0, or one root on this interval. So that's the first thing that we have to accomplish. And the way that we're going to accomplish that is by using the intermediate value theorem. So starting out here, to start with the intermediate value theorem, let's just evaluate our function at our two endpoints. So find what f of -2 equals, plugging in for every x. And what do we get for this? We get 16 minus 6 plus 1, so we get 11. And really the only thing that we're concerned about with that 11, whatever that number happens to be, we're just concerned that it's positive. It's greater than 0. Other endpoint, f of -1. Find that function value, and we get that's -1. And again, we're concerned whether or not that's greater than 0 or less than 0, and that's less than 0. So what we have right now is at the left endpoint, our function's positive, but at the right endpoint, it's negative. So this is pretty much what we need to show that using the intermediate value theorem that we will have a 0. We do have to say something about continuity because that's part of our intermediate value theorem. So what do we have? F of x, that is a polynomial function. So let's just write that down. So f of x is a polynomial function. And what that tells us automatically that it's continuous. So all of that right there, showing there, we know we have at least 1, 0 according to the intermediate value theorem. So let's just write that down. Thus, by intermediate value theorem, our function has at least 1, 0. On this closed interval we're concerning ourselves with. Going right through it, the second part we would have to show that we don't have more than 1, 0 on this closed interval. Thinking our way through this isn't part of the proof, but kind of side work where we're kind of thinking in our head. Our graph, only thing that we know about our graph, we're concerning ourselves with that small window from -2 to -1. All we know is that our function at -2 is 11, somewhere up there, somewhere it's positive, that's all we care about. And then f of -1, it's negative. So there's the kind of 2 points that we have. So that first step, we know our function, the graph of our function will cross our x-axis somewhere. So we do have at least 1, 0. What we have to make sure though is that we don't have any extrema in between there that might produce more than 1, 0. So what could that possibly look like? It could go down, but then it could come back up and down, and that's still a continuous function. That's fine, but it actually crosses our x-axis at 3 spots. So this is what we're trying to prove now, that this does not happen. What we want to show is it's just a straight shot from the f of -2 to f of -1. Straight shot. There's none of that behavior. So the way that we're going to do that is just by showing that our derivative in general is either always positive in this interval or always negative. So that's f prime of x is always positive or always negative. Seeing what 2 pieces of information we have, those function values at -2, -1. Looking at this, the slope between those lines, they are negative. That slope would be negative. So we want to ultimately go down, do some work, show our derivative is always negative and it doesn't come back up like this. We want to avoid that. So how are we going to do that? Second part, to show there's just that one spot where it crosses our x-axis. And the way that we're going to start with that, going back to the original problem, what they told us our intervals from -2 to -1. So let's start with that piece of the information. So x is in between -2 and -1. We're going to write that as an inequality, compound inequality. So that we used less than or equal to because we have a closed interval. And what we want to do is ultimately build in, do this work, build in, so we have our derivative in the inside these two inequalities. So we're starting with our function here. Let's side work. Let's see what our derivative is. So quickly doing that. We have our derivative. And what we want to do is ultimately build 4x cubed plus 3 in between our two inequality signs. So first thing that we want to do to accomplish this, let's cube our whole sentence here. So we can get an x cubed. So -2 cubed will be a -8. X cubed in the middle there, and then -1 cubed, that's -1. Then let's multiply the whole inequality here by 4. So -32 is less than or equal to our 4x cubed, less than or equal to -4. And then lastly, what we need is to add 3 to the left, the middle, right of this sentence. So adding 3, what does that result in? So now what we see, we have our 4x cubed plus 3 in between our inequality symbols there, and that's our derivative. So let's just replace that. And then reading this, what does this tell us? It tells us that if for our function on that interval from -2 to -1, our derivative values they run from -29 to -1. So that tells us that our derivative is always negative on this closed interval. So let's write that down as well. Thus, or therefore, our derivative is always negative on this interval. We could just write down on our closed interval -2, -1. And that tells us that we're just going to get that 1, 0. Here's all our proof. Let's just end it with a summary statement. So thus, f of x has exactly 1, 0 on our closed interval. And we are all done.